like analysis or probability kind of references.
Yeah.
The contractions or like border sampling is very more like multi-color methods, which I think not necessarily CS students might have covered. Not well.
Mac can do that.
Like that, I'm disadvantaged. I don't.
Only copy and paste. Then you get the slide
See what you're talking about the stuff we did last week.
Yeah, because I think it's not that intuitive to some people. It's like, you're reading a book where there's all these obscure references.
You come to me.
Okay, everyone is laughing like that.
Is it on record already?
Yeah.
Okay.
Yeah, I will take it as even sometimes in math we take it as just true first and later we come back and see what.
The three problems are crazy. Yeah.
Okay, so today we have Yong, Liang, and Ying, Kiat, as well as Praveen presenting. And we have some scribes on the Slack channel. So I think we can go ahead and start when you're ready. Here's Praveen. So yeah, you guys can take it away.
Could someone please check if the hangout is working?
I'm going to check now.
Oh, okay. So it's on already, right? Yes. Okay. Hello, good afternoon, everyone. So today we'll be talking about advanced policy gradients. My name is Yong Liang. After that, the rest of them will come up. So, okay, we can skip this, class 2 notes. Okay, so today's lecture. So we're gonna go through a couple of things. Why does policy gradient work? How we can look at policy gradient as some form of iteration. In Kiat, we'll have a discussion on how it becomes a constraint optimization problems, and then how we move onto natural gradients and trust regions. Okay, so 3 goals that we want to achieve today. Firstly is to understand the iteration view of policy gradient, how to analyze policy gradient improvements, and then what is the natural gradient and how do we use it. Okay, so let's recap policy gradient. So I think in a couple of weeks back, week 3 or week 4, actually we first discussed about policy gradients. That's where we introduced the reinforced algorithm. So basically what do? We sample a trajectory given a distribution, after which we compute the gradient of it, so the gradient of the reward, and then we just take a gradient ascent step. So on the slides I also included an explanation by Andre Karpati on policy gradients. So it's quite intuitive actually, and he has a simple code implementation, so you guys can check it out. So essentially what we're doing is we're talking about this model on the right here. So we have 3 steps. We want to generate samples from our policy. We want to fit a model, and then we want to try and improve the policy. So essentially, we can actually simplify this problem down to this approximation that we discussed previously, where we have the grad log pi of this pi will be a distribution, and then we have a reward to go, right? So once we had the reward to go, we have we have a couple of discussions about how do we estimate this value, right? We could either use it as a Q value, or we could look at it as function approximations, right? So, and then we also had the other discussions about baselines and how to reduce the variance of this prediction. Okay, so one other way that we were talking about in terms of value function approximation was in actor-critic algorithms. right, where we created function approximators for the value function. And then we had use those value functions to find the advantage. And then from there, we could just compute the gradient again, and then take our gradient ascent step. Okay, so why does policy gradient work? So the idea of policy gradient is quite simple. I mean, the loose theory that we sort of insinuated was that the fact that we are always taking these gradient steps, and hence if you take gradient steps by right, you should improve. Right, that's the same idea as with neural networks where you take gradient descent. So instead, we are doing gradient ascent here. So the idea is that we estimate this advantage function, and just to recap, advantage is basically the value function in the next step, subtract away the current value that you have. Right. So how much better is taking a certain action? How much better is it going to improve over what is your current value? Right. So we estimate this advantage for the current policy. And then with that advantage, we try and improve the policy. So we try and steer the policy towards actions that will take better values, right? So that's what we're trying to do. And it's sort of familiar into some form of iteration step where we constantly evaluate what's the advantage, and then we try and set the policies into the new ones, right? Okay, so how do we look at it as a sort of policy iteration kind of view? So first things first, we recall that we have this total value that we get, the reward, which is the expectation under a certain distribution parameterized by theta. So we have a trajectory tau, and then we are going to sum the rewards, and then we have a discount factor. Okay, so the claim that Sergey made here is that suppose we have some new policy parameterized by pi theta, right? So the idea is that we want to try and maximize this difference, right? So the reward that we get by following our new policy subtracted by the reward that we get in our current old policy, right? So we want to try to maximize that. And that's actually equivalent. He's going to prove, it's proven in this set of equation, but what he's going to do is that we're going to talk about, okay, by actually calculating this, what we are doing is that we're doing the expectation under this new policy, but we're going to use the advantage of the old policy to evaluate the actions. Right? So everyone sort of understand this idea, right? So because we actually don't have the new policy at this point of time, we haven't calculated any new policy, right? We don't have a new guide. But what we do is that we have samples of our old trajectories, right? So what we're going to do is we're going to evaluate the advantage of the old policy, and then in doing so, it's actually the same as maximizing this expectation, right? So let's go through the mathematical derivation. So first, we define that we have this new policy theta prime, and then we have a sort of reward from it, and then we're taking a difference. So what we can do is that we can expand out the j theta, which is the same as the expectation for a given policy p for the initial state. And then that's the same as doing the expectation for this v pi theta from the same initial state. Okay? And we can actually change this to be for any trajectory, because for all trajectories, we will chances are we will start from the same initial state, right? So for any given trajectory, this conversion is actually true, right? So depending on whatever policy I take, we will start from the same initial state, all right? Now, what? In the third step, what we're going to go through is that let's do a telescoping sum. So what we're going to do here is that we're going to take this O value function. We're going to sum it from 0 to infinity. And then we're going to subtract away at time step t equals to 1. So I put the mathematical expansion on the right. So they're actually both equivalent. We haven't actually done anything here, right? Just algebraic manipulation. And what we're going to do next is we're going to take out the minus sign, right, from the equation. We're going to take this minus sign, we're going to bring it out. And then we're going to have a simplification here. So if I can just increase this t over here, this t representation to t plus 1, we actually get the same summation, right? From t equals to 0 to t to infinity. And then we just add extra gamma, and we can simplify this algebraic expression to be the gamma to the power t multiplied by this next step called reward minus the current state at time t. Okay? And if we expand the j theta, it's the same as the expectation under theta prime for trajectory tau. and the reward, right? Same as this given original equation of what is the total reward that we're going to achieve. And then we can combine these together because they're under the same expectation for the same trajectory, right? Which is this new data prime. And we can simplify this further into the advantage function, right? So if you follow here, what we can do is we can just sum this all up together. We will have the reward plus the value of the next step that we're going to take, subtract away the value of the current step, and that's actually just the advantage function. And we still have our gamma to the power t on the outside. Everyone can follow so far, right? Yeah.
Sure, it's a big question.
Yeah. No stupid question.
First, but we merged the two expectations.
Yeah.
Second last time.
Yeah.
We're bringing from t equals to 1 equals to start from t equals 0, right?
Yeah.
Then surely the reward be st
st plus 1 at plus.
the reward. That's the first part. Because now we are like,
That's a good spot, actually. I didn't see that.
Talking about the first term in the
Yeah.
last, second line is on st, at.
I actually think that it's a typo. Yeah, I actually think it's a typo because when you do expectation for that trajectory tau, you calculate from t equals to 0 to infinity. Right, from the initial state all the way to the end state. So I actually think that this is a typo. Yeah, I think this should be 0. Yeah. He didn't point that out. I changed the other parts of the slide that he spotted errors, but I think that that should be error because it doesn't make sense if he starts from t equals to 1. Yeah, it doesn't make sense to start from t equals to 1 because, I mean, if we do that same expansion over here also, we should have, yeah, this is also t equals 0. Yeah, so yeah. Correct. That's actually a good spot. I didn't see that. But yeah, I don't think it makes sense that it's t equals to 1. I think that's t equals to 0. Maybe we can just note that down in the scribe and then just ask. Yeah, but if I'm not wrong, yeah, doesn't make sense to start from t equals to 1. Right. Okay, so now we have a expectation under our new policy that we still don't know actually, right? But we have the advantage function that's following our old policy, right? So now, this is the formulation that we had. So you have expectation under pi theta prime, but you have an advantage under pi theta. Advantage under pi theta is something that we can calculate because we have samples up to this point, right? We run our certain policies, we collect data, but we do not have pi theta prime. So taking the expectation under pi theta prime is a bit troublesome, right? Because we don't know the data samples. So you just did a trick here, which I think it's the same trick that we saw in the policy gradients, where we bring out the sum. And when we bring out the sum, what happens is that we marginalize, right? So now we actually have the expectation under p theta prime for a certain state, and we've marginalized the inside part, right, of an action at point time t, right, for this pi theta prime theta, given for action given a state. And this is the advantage function, right? So from here, we can actually convert this pi theta prime by using importance sampling, right? And some people, a question asked in the class was that, why can't we just do importance sampling on this entire term instead? Because for this entire term, we are calculating the expectation of the entire trajectory given a policy that's parameterized by theta prime. Now, when we want to take expectation, if you want to convert, you're basically taking this this distribution. So if you calculate across the entire trajectory, if the trajectory is infinitely long, the probabilities are going to multiply by each other, and they're going to just decay down to 0, right? But under this marginalization, we are actually only marginalizing across one state, one point of time, which is at time t. Hence, he uses the importance sampling on the inside rather than the outside, right? Okay, so then he asked the question, can we actually just use pi theta, p theta st instead, which is, can we just use the current policy, right, instead of using that new policy that we have no idea about, right? So this part is a bit troublesome, and because we don't have our new policy, we basically can't do that summation. So what he does is that, okay, let's this whole representation just be set by a bar, and we're going to say that j theta prime minus j theta is approximately equal to this advantage over here, but it'll be under the O policy. So why do we want this to be true? It's because if we can change this expectation to be under pi theta, we can just sample from our current space. We can just take the current data samples that we have, and we can just calculate them, right? We can solve that problem, right? So yeah, we can just generate the samples that we want, right? So the next question, so that's actually all there is in policy gradients as an iterative example, right? So recall that what we're trying to do is we're trying to just use whatever we have right now in our current policy. What we're going to do is that we're going to take expectation, right? And then we're going to take expectation for each, and then we're going to evaluate the advantage using our O policy. And then now what we're trying to do is that, okay, we can't take expectation across this new policy that we have no idea about. So why don't we do the expectation on the O policy? But there is some approximation that's involved, right? So that approximation Kiat will go through, which is basically what does it mean to be close, right? Because if we're saying that j theta prime and j theta is approximately equal to this advantage under the O policy, what does it actually mean for the two policies to be close? Because if two policies are close means you probably will take similar actions, right? Yeah, so Kiat will go through that bounding problem. Yeah.
So I have a question in the slide where they derive the claim.
That's right.
So in the second equation,
yeah.
So he says that we estimate j of theta as expectation over our initial state distribution of our value function. So that is the we substitute j theta for this.
This part here, right? Yeah. Okay.
And then the step we take is he says that we can replace this initial distribution by taking a trajectory in any arbitrary distribution by theta prime. So we can take this step provided that its initial distribution are the same. So that is what he said in the lecture. But what does it mean exactly?
Repeat your last sentence.
So he said that it's provided its initial distribution is the same.
Yeah. Okay.
So we can take any probability distribution p theta prime, provided its initial distribution is same.
Okay. I think that means is that just only for the initial state. Because for the initial state, that initialization probability, so the probability that you go into the initial state will be the same for all trajectories. Yeah, so that's what I understood. That's why he can just casually change this distribution under S0 into any trajectory. Yeah, so from my understanding is that the probability of entering that initial state for all different trajectories is the same. But that future trajectory, that value function that goes on after that can change from trajectory to trajectory or different kinds of policies. Yeah, so that's why I think he did this trick. And basically this whole part here, right? This whole part is also just v pi theta of S0, right? We're just expressing it with different algebraic representations, but actually this whole thing is just the same value function for any trajectory given S0. Yeah.
So you haven't taken any actions yet. So it's just the initial distribution where you would find yourself in the world, right? Which state it is. No actions yet, so all policies are this. All policies have the same initial distribution because that's defined by the world, not by the policy.
Yeah.
Okay. Sorry, I have a question.
Yeah.
More general question.
Yeah.
Oh, maybe like I can give like my understanding of this assumption, which is let's say you're playing chess and like you're making a learning algorithm to play chess. And so in the game of chess, you start 50% white, 50% black. White starts first. So like the initial state is white or black with 50-50 the distribution state. But let's say like if the rule is such that the higher elo person goes first, then when you change your policy, your elo rating changes, and you actually like as a result start more. Then the initial distribution is changing. Then this is something that's not cool. So it's saying that like the initial distribution. sorry. So my question is like, so I believe this whole lecture is about trying to explain like the policy gradient is like possible. It's doable and it converges, right? But then,
Yeah.
so at this step, he's trying to say that theta prime does not give us a distribution. Or rather, we cannot assume that we have a distribution for theta prime yet. But why is that assumption? Because like when we do a policy gradient step and we get a new theta prime, we can use that to generate a bunch of like distribution for us.
Yes, you can. But when you have, let's say your agent runs to a certain point, I think his explanation is that if you generate a new theta prime, to get the data samples up to the time t again, you have to restart your whole trajectory. So you're constantly repeating, doing one, and then you repeat. You do one, and then you repeat. So there's it becomes in that sense, you have to repeat your experiments every time, and you can't utilize whatever data that you have collected on your original samples.
Isn't that rollout? I mean, like, isn't that a policy gradient? You run the policy gradient, and then you do a new rollout, and then after that, you compute based on that new distribution.
I don't quite understand the question.
Right. So here, like, is addressing the challenge that we don't have theta primes trajectory. We don't have the tau for theta prime, which is why that part in front, which is sampling a distribution out of the probability of theta prime tau is a problem. But let's say we were to use policy gradient to train, then what we're actually doing is once we do a gradient descent step, and then we have a new rollout that gives us a new bunch of samples. So we actually do have the distribution now.
So this is before you get theta prime.
So,
Right, so you don't know yet because you haven't got theta prime yet. It's deriving this.
but that has, but if we do gradient descent, we will have theta prime.
After you do the descent step, okay, we'll have.
So he's saying we shouldn't do the gradient descent first.
But you don't have it to do it.
So it's someone like chicken and it. If you want the, yeah, if you want your data,
You haven't done it yet.
You calculate something. Like something,
Yeah.
by right you use data prime, but
You haven't done
because
it
you don't have data prime, so you use
Oh,
data
understand.
instead. And I think I'm doing some approximation where they use that data to calculate. Yeah.
He's saying that we need this to calculate theta.
Yeah. So he's trying to get to the class region policy optimization algorithm, trying to derive that. And as part of the derivation, he wants to ask, which data prime should I choose?
Okay.
Right. So this is towards getting there.
Okay, thanks.
So before we get to the next presenter, are there any questions from remote? So we have quite a few number of people on remote. Any comments or confusions? I guess we're okay. All right, so let's thank our first presenter.
Hi, so my part is basically about in a way proving the claim that the distribution probability of is close when the two policies are close. Basically, when can you use theta instead of theta prime to calculate theta? So it's about finding that bound or that constraint. This one it's so first it's about what does it mean to be close? I mean, for the two policy to be close. He start by assuming that pi theta it's a deterministic. I mean, he didn't know that this is not a realistic thing because the problem. I mean, it's not. It will be stochastic, but he started with this first because it's easier to analyze, and then the next slide will talk about when pi theta it's stochastic. So he defined that the define pi theta prime as close to pi theta if the probability that the action taken under pi theta prime is not the action taken under pi data, it's bounded. So basically the probability that the two actions are not the same, it's bounded by epsilon. So that's his definition of being close, and he said that this is quite similar to the imitation learning from the earlier series of videos and lectures. So a lot of it is from there. Next, we talk about this probability of distribution, the probability distribution under theta prime at state t, and for this there are actually two terms. So that's the first term and then the second term. So the first term is the probability when make no mistakes, and that means that at every step the probability distribution is actually the same, and that probability is 1 minus epsilon at time step 1 multiplied by 1 minus epsilon time step 2, so on and so forth until t. That's where you get this 1 minus epsilon to the power of t. So this is the make no mistake part, and 1 minus this probability will be the other distribution where you make one or more mistakes. But we don't really know what this some other distribution is. So now now that we have this probability distribution for theta at time step t, I mean which is this box here. I mean, if you rearrange all the terms, ultimately you end up with this. So I think you just take some of this, you add in the probability distribution of theta and the time step t. So you rearrange them, you'll be this. And for this one, it's actually bounded by 2 times 1 minus epsilon t, because we don't know the distribution, the probability distribution of p mistakes, so we assume the worst. So in this case, the worst will be 2. That means this total variation divergence is actually maximum is 2. So that's why you have a less than or equal to 2 times 1 minus epsilon power of t. And using this identity, I mean, you can further summarize it to less than 2 times epsilon times t.
Sorry.
Yes.
Let me understand why upper bound is 2, because first term is p mistake minus p theta. So I suppose this is a probability distribution, right? It ranging from value should be between 0 to 1, right? In that case, why p mistake minus p theta maximum value could be 2? I suppose it should be 1. Am I right?
No, because the two distributions can be completely disjoint, right? So I think he makes a point in the previous lecture. Let's say in the case of a discrete distribution, you have one action have probability 1, and then the other, the p mistake would have another different action have probability, right? Then if you take a look at the difference between them, you would have to have 1 and then minus 1, right? Because the two distributions are completely disjoint, right? I also had this question, but then I thought about it. Okay, so you can draw this out, right? So if you have a probability distribution, right? Let's say this is your first policy. Let's say this is your state, right? And then if you have another distribution that's completely equal probability.
Because I think it's
And then have 1.
This notation seems a bit odd. It's probably talking about the norm rather than it's integrating over all.
Yeah, he did say the absolute value doesn't actually stand for absolute value in one of his lectures.
A one norm.
Yeah. Was there a question online? I heard some hustling. Nope. Okay.
What's the mouse shortcut for this?
It's F1. It doesn't seem to be working on slide mode. So yeah.
So next we look at the what if pi theta is an arbitrary distribution rather than a deterministic one in the previous slide. So in this case, there's a different definition for the two policy to be close together. So in this case, they are close if the total variation divergence between the two action distribution is bounded by epsilon for all the state. And if we have this bound, it means we can still bound the probability that pi theta prime make a mistake. So Sergey also mentioned what it means by making a mistake in the case of probability distribution. So he used the analogy of a pseudo-random number generator, where if you take the same random seed twice and then you run the same stochastic policy, you get exactly the same action. So in this case, you're making a mistake if you use the same random seed twice and then you run it under pi theta and pi theta and then prime theta prime and compare them. What's the probability that they will agree? So, and I mean, this is a lemma he uses to eventually derive at this part where the mistake or the difference is actually bounded by epsilon. So okay, for this, and then this part here is actually quite similar to the previous one because I mean, in a way it follows from this part where there's the pi theta prime and the difference between them, it's bounded by epsilon. Okay, this part. Okay. So the earlier two slides was about bounding the distribution graph. So here, but what we really want is to know, understand the objective and not just the state distribution. So in other words, we want to know whether it's okay to replace that theta prime with theta, and what will it do to the objective. So as a recap, I mean the objective is that j theta prime minus j theta, and it's actually given here. But before that, I mean, this is a slightly more generic case to show that the bound on the expectation. So in this case, you're using some generic score function f of st here, and we'll substitute. I mean, this equation here is just a definition of expectation, and I mean, if you notice, I mean, using a different probability distribution, say that the original one, it's actually more than or equals to the other one minus the which part? Okay, so if you have an expectation of some state distribution of p theta prime of some function s of t, and it's equal to the sum of the product of the probabilities and function, so this is the definition, and then you will bound the expectation by under them, and then times this maximum value of f that of this maximum value f times that t. So assuming f is always positive. So it's I think what Sergey said is this is saying like every time you move away or vary from p theta prime, this is the worst thing that can happen. So in this case, I mean, this is a bound. when you use a different probability distribution. So now if we change this to using the objective function, which is in this box here, I mean, if you just replace the relevant term, basically it comes up to this whole set of inequalities. So this is the correct objective, meaning you use the data prime and you use data. And then remember, we wanted to use data because we don't have data prime. So you want to use data, you have to, this is the cost of approximating. That means the cost of using data instead of data prime in terms of the objective function or the expectation. And for this so-called cost of approximation, it's 2 times epsilon times t times some constant, and this constant, we can explain it as it's to the order of capital T times Rmax, where Rmax is the largest reward you can get, assuming T is a finite number. But if T is infinite, I mean the horizon is infinite, then will be Rmax divided by 1 minus gamma, because 1 over 1 minus gamma is the effective discount.
Questions about that so far?
So basically, the second term is how much suboptimality that you incur by doing the approximation of using theta instead of theta prime.
I have a simple question. So capital T means that like the maximum number of times.
Yeah,
yes.
That's the iteration all the way out. So that's the maximal time step for the bounded horizon.
Oh. So if it's okay, I'll move on to the next slide. So this slide is about using a more convenient bound instead of the total variation divergence. So basically, you can use a different bound using the KL divergence, which apparently it's a lot better because it works much better with a lot of the distribution. So this step is more, I guess in a way, it's more like a practical tip when you implement this, because using the KL divergence, it's better than the total variation divergence. I mean, this is the formula for the KL divergence.
I think he explained that, KL divergence used in many applications. There's a lot of nice properties of KL divergence. So it's just a more convenient form to work with, right?
So using the KL divergence, I mean, this would be the new, more convenient bound, as given here. So the next thing is, I mean, we bring all this together, then what does it mean to optimize the objective? So if you recall, I mean, this whole string here, this is the objective, the approximate objective, the J theta prime minus J theta approximate, because you're using theta instead of theta prime. And you want to find the argmax of theta prime. So essentially, really, is you want to optimize this. But the challenge, I mean, he said that you can't just throw this into the TensorFlow or whatever to find out, because there's actually a constraint. So the challenge is how to fit in the constraint in order to solve or find out what theta prime to compute the constraint. So is there a way of finding or imposing the constraint, and then with that you can then put it into a Friedel TensorFlow or whatever to solve. I mean, you also made the point that for small enough, if the value of epsilon is small enough, then it's guaranteed to improve the objective value. Okay, now, so then he talked about how to enforce that constraint. So what is the algorithm to do that? So there are a few things to note. So one is he said we can use the Lagrangian to express an optimization problem as well as the constraint. So this is that whole Lagrangian. So it's given here. So in order to enforce the constraint and to be able to find the optimal theta prime, the algo is it's here. It's fairly, I mean, it seems straightforward. So the first, he called it also the dual gradient descent because actually doing gradient descent on two parameters, the pi theta, and then after that the lambda. So the idea is that in step one, you maximize this thing here with respect to theta prime. He said that ideally, I mean, you should run it until convergence, but practically, you can just do this for a few grad steps and it's sufficient. I mean, practically, so it saves time. And then once you do that, you can find a gradient for lambda and update lambda, and then you kind of iterate to find the optimal theta prime. I mean, he did say that this dual gradient descent, I mean, the derivation of all that will come in a subsequent lecture. So we can go about saying how it exactly will work.
So you guys are comfortable with the intuition behind what's going on here? But you're optimizing against two variables, each one you can take and on. What about the intuition that he raises here? Radius lambda, pi radius much. Also, are you guys all familiar with Lagrangian optimization and multiplier? The whole idea is that you have a value that you want to optimize, but there's some constraints. So whenever there's constraints, you need some form of constraint satisfaction, and you can do that in the Lagrangian framework. Everyone happy with that? Any questions or comments, either here in the room or online? Okay.
So yeah, basically, it's my understanding is that the second term is like to penalize like objective function with like violating the constraint.
The second term meaning
yeah, like
alpha.
Multiply, like
this one.
Okay, I mean like lambda multiply like tail divergence of the like pi theta prime and the pi theta.
Yeah, the alpha, not lambda. Sorry, because lambda is the parameter that you're updating, right?
Yeah.
And then you have a multiplier, some decay factor. You're
So
learning.
like violating constraint so much, then like object function is like getting the smaller. So this is my
I think that's right.
Can I clarify something on the previous slide? Like to go up to the founding objective value. One more. Like the summation for the first inequality. Okay, the second inequality. Yeah, the summation is it over the whole term? Is it over just like the first part for the minus sign?
I think it's this
First term.
because it's a bound. Because I mean, in a way, it's like from here, then you approximate to this, and then the cost of approximation is this one. I don't know. Or maybe
The second one has an ST there that is. Because so the derivation doesn't make sense because right now he's using minus 2 epsilon t, right? But at the bottom, if you would like the bottom, there's a summation over t. So if you were to sub in st, right, it doesn't fit.
it's like a whole.
If it's the whole, that means he's missing a summation term on the second inequality. The bottom,
This one.
yeah, this one.
In the lecture, he said that even if we make one mistake, then this is the maximum penalty.
Right. Yeah, on one state. But like, yeah, so I'm just curious, I'm just not sure whether like the inequalities for like the summation over ST is for the entire expression or just like the first part of this.
That's why we get a T there.
Okay.
If it's over entire thing, we get a T. So as we step, this thing worsens. It's 2E T, right? As we step, we are diverging from the probabilist.
But there's just some you're just substituting the top term in. So
Let's do epsilon.
Yeah, you're just substituting 2 epsilon T into the
summation over ST then.
2 epsilon T. On top is already 2 epsilon T.
No, what I think what Praveen is saying is this is 2 epsilon, right? And then when you take it over all the time steps, you have not enough part. Is that right?
Oh yeah, that's what I was saying. But so we got this from the previous 2 epsilon T.
You are saying you are missing a summation.
Yeah.
That's probably because this notation, you should do a variation on this L1 now. You should have 2 lines on the L1 line.
Oh,
Here.
This is notation.
There's
some
some
lines
implicit.
Oh, this is L1 line.
Okay.
Right, if there's 2 lines, then you will have T.
If it's 2 lines, then it's already a sum over all state, right?
Yes.
Okay.
Yes.
Okay.
This is notation.
Right. Then the bottom.
Then this one should be a summation.
Came out from. Yes, confusing notation.
Math is generally, I mean, it's a higher order.
Because it's already referring to the whole.
Yeah, it's implicit inside his notation.
Sorry, back to the lambda at the end.
So wait, can we go back and just summarize nicely and neatly so that we're sure in our scribe as well as for those people online what's going on here? It's because of these absolute value signs are actually being used as the L1 and that because of that the summation is implicit over all times that.
Overall states.
Overall states, right? Yeah, sorry. Overall states. And how do we get to here?
Yeah. So that's
So this is also.
Yes, this is also.
How do we use the top equation to get to the bottom, the one that is minus summation 2 epsilon? Yeah. How do we get from? How do we fit this in to get that?
The second equation is for just expectation over probability state, and here we have what our objective is a summation
This
over
one or
T.
this one?
Yeah, this one is summation T. So that's why that T, summation T comes.
Okay. Okay. Right. Okay.
Okay, go to the other question.
Yeah, so just a quick clarification. So when it says the equation is raised lambda greater by much, what is it saying that if it's violated too much, it means that our epsilon is
This value will be high.
Yeah, because if the constraint is violated too much, right?
Yes.
It'll be lambda plus alpha times a positive number.
Actually,
So you're raising your lambda.
yeah,
But if it's well behaved, then
so what is the intuition behind what's the cause of lambda being the constraint being right? Because our epsilon is too small. Like we have a very tight epsilon.
So when we try to maximize the Lagrangian there with respect to theta, then we maximize this, but that violates our constraint, and that we check on the second one, and then we update lambda. And if a constraint is violated, lambda increases, then that goes again into the equation, and it's penalized. That means the next time we try to maximize, it has a with some other.
Basically,
That's the test.
so because the constraint right, so it's trying to say that whenever the KL divergence is large, since epsilon, then we put more weightage on lambda to kind of put more pressure on this. So every time it exceeds the constraint satisfaction will ask it to put more weightage on it so that it becomes more and more important to satisfy the constraint over time.
How does this minus lambda helps in changing? Because we are only changing theta in the first step, right? When we're trying to maximize the Lagrangian, we change theta prime. How does this term help to bring it back into the constraint?
There's a theta prime.
There's a theta prime over the policy. That's why you are also affected.
Okay. So we have more penalties for if the theta prime is violating, then we increase lambda. Okay.
Everyone following, can we put it into like lay terms? We're doing gradient descent. I mean, we cannot understand all mathematically the variables, but then you're trying to step through the logic of doing dual gradient descent. You have two different landscapes, and you're doing ascent or descent. Then yeah.
So we have an optimization problem. We want to maximize this objective, but we also have a constraint. So we do dual gradient descent, where in first step we try to maximize our this expression, which also has the constraint, we try to maximize that by changing our parameter. Then we take a gradient step in trying to bring it back to inside our constraint. So we are doing a gradient step on two sets of parameters independent. So that also optimizes the value and also makes it does not violate the constraint.
Sorry, correct me if I'm wrong. So I'm seeing like objective function L, theta prime, and lambda, and so first term, like as theta prime getting bigger, then first term is also getting bigger. Unlike like not necessarily. I mean like sorry. So I'm saying that like there are two terms on this objective function. And okay, so this is the first term of this objective function. If like we increase the theta prime, this first term like like a proportional relationship.
Yeah, I think if you find a better theta prime, the first term will increase because you find a better policy. Hence your expectation increases.
Okay, so which means like basically like more like bigger theta prime should be better.
Yeah, so we want to find a better policy.
Yeah, but we have a constraint such like so which means we have a second term to pass. My point is that like bigger theta prime is better.
Yes.
But we cannot like set any like a big value for the theta prime because we have a second term.
Not really bigger value is better, but just it depends. Yeah, it depends on because the data is the one that's governing your policy, right? So it's not just that the big value of theta is good, it's just that yes, you need certain value of theta. That's why you find it.
The second term is basically saying that we don't want our new policy to stray from the old policy too much. And that comes from the previous introduction on the policy gradient, right? You sort of formulated it as some form of gradient. Then we say, okay, we have this gradient, but we want to enforce a certain constraint, and that certain constraint was given by the KL divergence, right? And then we substitute it in, and then we say, oh, there's some form of suboptimality that happens when we try and change the expectation from theta prime to theta now. Yeah. And hence, to satisfy that constraint, we don't want our new policy to stray too far from the old policy, but we still want to find a slightly better policy. That's my understanding thus far. And that's equivalent to maximizing a Lagrangian over two parameters now. Yeah. Rather than do that classic gradient sense that now we are actually maximizing a Lagrangian, which is equivalent to doing gradient ascent. Yeah. That's my understanding.
Yeah, so I think that intuition is really helpful, right? That you understand from a geometric point of view what is going on, right? So you have an optimization problem for constraint, and the constraint is dynamically updated because theta and theta prime are moving at every time step. So what I like to think of it is like the constraint is like a dog walker with a dog. Okay, so you have a dog walker who's theta prime, or theta, right? And you're looking for theta to optimize theta, but your dog can only go so far away because the leash is your constraint. See? I let you go in a direction that's optimal, but you can't get that far. And then when I update my timestamp, the dog walker moves, so I'm moving my policy, but then my dog can go around in a circle again. So it's being updated and moving around in that space.
Okay, I'll just move on. I think that's. I'm just as a review of the. Let's just slide. I mean, to do policy gradient, it's essentially policy iteration. You have to evaluate the advantage of the old policy by maximizing, and so that you can have a new policy. But to do that, the correct thing is you want to optimize the expected advantage. But as mentioned by Yong, you don't have the theta prime, so we need the old policy, and to use the old policy, to assume that or rather to approximate the new policy theta prime with theta, you need a certain constraint, and so basically it results in this constraint optimization problem.
In the previous slide, am I wrong in saying that this makes it on policy because we are using the previous policy?
Yeah, it's the
on policy.
I think that's a feature as well as a disadvantage, right? To policy, right? Because we've heard in the Q value lecture that many times you don't want to throw away samples that you generated from a previous rollout, so you want an off policy way of doing it, and then you can still use important sampling for that. But then, yeah, the way that we're talking about is still on policy, right?
So I want to try to tie this back to the policy gradient lecture we had actually.
Yeah, please do.
How this attempts that we can use a solver to solve for a data that is given the epsilon bound, and that results in us doing some form of
From what I understand, the policy gradient lecture gave the vanilla algorithm, right? And then towards the end of that lecture, he says, well, even though this is really nice and all, all things don't work out in the case where you're looking at infinite horizons and continuous states, right? Am I getting that right? Okay, so in that case, is all hope lost, right? And the answer to that is no. If you can epsilon bound how things are going, and you can still optimize within a very constrained framework. So you can solve for a new policy, but as already pointed out in lecture, you're not solving exactly. You're just doing an approximate, right? You just do it for a couple time steps, and then you have an approximate way of doing it, and then you move to the next data. That's what I was
This
saying.
is not that policy gradient, like gradient descent that did that capture. This is completely different way to find it. Because that one that was the fixed thing. That problem.
So I think that what the matrix is we don't know the theta prime. So we bound it with some error and then try to calculate.
It sounds like the earlier one is almost like an ideal theoretical case. And this one is okay. In reality, there's some problem with that. This is how you actually try to implement it in.
A different algorithm. There a description on the algorithm? I remember, but in the previous slide, there's a description. Step 1 and 2, that's the new algorithm. So it's a different.
Because the policy, the reinforced algorithm breaks down. That's why. Does it slow? Does it work?
I guess this one, they are trying to make sure it's sort of a monotonic. Every time, every data to data prime is sort of a monotonic. Policy as a reinforced is very noisy gradient. So this gradient descent, very noisy gradient. This is not quite gradient descent. It's saying every time I go from theta to theta prime, I sort of want to make sure it's an equal to. It's a different output, but not stochastic, not really stochastic gradient descent.
It's not vanilla gradient descent, right? It's gradient descent with a sanity check or something like that.
Yeah.
So the whole rationale behind this is to make the policy gradient more practically effective, I guess. Okay, so we finished the second part. So thank our presenter.
So till now, what we did was we said that if we have a bound on our probability state probability distribution, then we can improve our theta if we have a bound on the two policy distributions. So our now we have to optimize this with the bound. So so to optimize, we have to take the grade. So this part here is our objective. So let's denote it by a bar theta prime. So we have to take to optimize this. We do a gradient on that value, and then we take argmax. We say which theta prime maximizes this objective. So we have to compute the gradient. So So here we can use Taylor approximation to compute this gradient. So so we have to calculate this complicated function on at this value. So for that we can use Taylor approximation. So so as in this slide, if this is a complex function, if we choose a small window and we approximate it to this linear line, then we still can say that we can take step in this direction because the curve is going there, and we still get an optimal theta even after approximating. So I think these slides are to make this algorithm practical. So Taylor approximation, if f is quickly, it's we can approximate function f of x at point A by using the Taylor expansion. And here he suggests that we use the first order approximation. So we keep only the first two terms and we ignore the rest of the terms. That means, so if the window is very small, the square terms are negligible. So we do a, sorry, it's, yeah, first order approximation. So, so what we do is, so we substitute this, this comes from our policy gradient lecture derivation. So we have to take a gradient on our objective. So we did the same thing in the policy gradient. I put a slide from the previous. So we use this identity. So quickly to go through it, if j theta is our objective, then the expectation, we can write it in form of integral, the distribution, our probability distribution over the rewards. And then, so using this identity, we can substitute grad. So when we take the gradient of the objective, we can put the gradient inside, and then we substitute with this identity, and then we get a expectation over the grad of log of our probability distribution. Grad of a bar. And then, since we said that our probabilities don't diverge much, then we can cancel these two. Can we cancel these two because our bound is that between those two probability distribution is bounded by epsilon? Or
can you point with the mouse?
Okay, sorry.
Easier.
Yes. Because what our bound is, if I can go back. So so these two, our bound is this. So on our two distribution, our bound is this. So in this slide,
you're not cancelling it because of the bound. You're cancelling it because you're using the same distribution. So like the top equation is if there is for if there's two distribution, but if your second distribution, the one with the prime is equivalent, is the same as the one without the prime, then you can just kind of cancel it. Yes.
Oh, okay.
Yeah, and you can see this line, the front there, it actually says it's actually theta without theta prime. So now
we're using theta instead.
Yeah,
So here, since the gradient equation is the same, so can we use that to improve our theta. So the thing here is that if we try to improve our theta using this step uh, uh, by this gradient, so the change in the theta parameters may change the probability distribution drastically. And our constraint is that over these two distribution, it should be bounded by epsilon. So we cannot use these improvement on theta. So because this may change drastically. Yeah. So some probability change. Yeah. So the theta, the probabilities that depend on theta, some parameters can change the distribution. Uh, so in this diagram, it says that if we take a step from the point in center, if we take a step inside this circle, then it may improve our objective, but the distribution may be completely different than the previous one, and that does not hold our constraints. So here we are trying to make a bound on theta. So that means when we take a step, let's not take a step outside a circle that is bounded by theta. So we are trying to introduce a different bound. Yeah. So these bounds are different. So in our gradient, policy gradient, the bound is on theta, whereas in this new algorithm, the bound is on the probability distribution of our policy. So since these bounds are not same, so we want to try to make some uh, try to make, so when we take a better step in theta space, then we also have to try to not change pi drastically. So to make it comparable, we do this analysis. So we say that so we use this Fisher information matrix. So this is an approximation of the KL divergence. I don't understand this equation, and I think he said it will be covered later. But what I understand from this is that we are changing theta, but we're using this Fisher information matrix, which has the information that which parameters in theta change our distribution. And it is estimated with this equation. So maybe if someone understands these two equations, they can elaborate. So in the previous slide, the formula for a KL divergence is expectation of log the first probability distribution or the second probability distribution. From there, then said we can do a second order because our constraint is on a quadratic on a theta space. Here we can take a second order term from the Taylor expansion and use this Fisher information matrix to scale our theta changes. So anybody needs to say something about this? So I got some things from Wikipedia about what is Fisher information. So it says that if we have a random variable x which is dependent on parameter theta, then a Fisher information carries information which theta can change that random the value of that random variable. So if f is peak sharply with respect to theta, so we can say which value of theta is responsible. So what we're trying to do here is, since we cannot take a step from theta even inside that circle, we we take a step knowing this Fisher information, and that modifies that circle in theta space to this ellipse. That means we change theta, but we do not change the distribution so much, and that is in this F matrix. And this is called the natural gradient, because we're improving theta without changing the distribution much.
I think if you go up, yeah, it's like right. So we are trying to change the KL divergent into the bottom form, so that yeah, that's what they're trying to do. But so they are saying that the KL divergent can be approximated with the Fisher information matrix, right? So they essentially just substituted the Fisher information matrix into the KL divergence, so that it becomes like such that that Fisher information matrix, that second order Taylor extension is less than epsilon, I think, and then that that is like the I believe is equivalent to like the second is equivalent to theta minus theta prime. Yeah.
It brings it closer to that form.
Yeah.
Because now you have the theta prime minus theta transpose times the theta prime minus theta with the Fisher information matrix in the middle. So you get a form that is close to actually what you have in the theta minus theta prime in the two norm.
I guess if Fisher information is can be kind of decomposed into two matrix that is transposed of each other, then actually it becomes directly the form. Because the 1/2 constraint can be pushed to the epsilon side, right? Not sure. I'm guessing here. But yeah, so essentially that's what they're trying to do. And then like by doing that, like if you were to approximate the KL divergence with this expression, you get the new gradient, which is the inverse of the Fisher information matrix times the whole gradient. So when they say natural gradient, I'm not sure, but I think they refers to essentially the inverse of Fisher matrix multiplied by the whole gradient. Yeah. That term as a whole is called a natural gradient.
One thing also is that, go back to that slide again. Look at it, the KL divergence between theta prime and theta, you don't actually have the distribution of theta prime still, right? So if you don't have the distribution of theta prime, you can't calculate KL divergence. So instead of calculating the KL divergence, I think what he does is he tries to calculate using this L2 norm of theta minus theta prime. Then you can estimate the KL divergence via the Fisher information matrix. If you look at the Fisher information matrix definition it gives, that's actually just the covariance matrix between the gradients. So it's the covariance matrix between how the gradients will change with the data matrix, right? Because it will be a data by data size, right? And that's just covariance.
It's symmetrical.
Yeah, the F, right? F equals to expectation with grad dot I times grad dot I transpose, right? Yeah. So that is actually just covariance.
Yeah, right.
Data covariance. So how does the expectation vary for this covariance matrix?
So that if that is symmetrical.
Yes, correct. It should be symmetrical because it's a covariance, but covariance between data in space. Right. So that tells you that given like a different kinds of pairs of data, how that expectation of this pi data will change. That's why I think Praveen mentioned about you don't change that the distribution too much because you don't want to take data that changes that expectation too much. Yeah, so that's what I kind of get away from this slide. And that's equivalent to sort of like the KL divergence between the two policies. And then, so hence now we finally have a bound, right? We finally have a calculation for the bound.
So Sergey here says that So it's also practical to use natural gradient for this example. Not just that we are trying to satisfy bound, but it's also practical because in this example, so to explain this, I don't completely understand this, but I'll go through it. So the problem is that we have a 1D space and we're trying to reach a point, and we can take continuous actions. We can define our reward as the distance from our current the goal plus the size of the actions. That means we cannot take big actions. And then if we use this simple policy, which says that can anybody explain this what this policy is saying? It has two parameters, k and sigma, and then we say that given a state st, which action to take. Can anybody explain this policy?
We try as a group. Let's try to recap what we understand about what's been lectured on so far, right? So to go back to the last slide where we're talking about the Fisher information matrix, why are we using that? What's the high level rationale for what we're doing? I put some notes from various blogs on the shared draft worksheet, so you guys can take a look at that. But basically, why is because a mismatch, which is what Praveen just showed on the last slide with all the gradients and the errors. Right? So we want to estimate it better, right? So if you use vanilla policy gradient, you get something like A, and we really want something more like B that's more reflective of how to optimize. Otherwise, we use the vanilla policy gradients, we'll get something like what we have on the right-hand side, right? Where we're zigzagging, we're trying to optimize, go towards the middle, go from the outside towards the center optimum point, but we're going to be bouncing back and forth. Right, so the Fisher information matrix is measuring the distance more accurately because the policy space isn't flat and uniform, right? And so we can use it as a drop-in replacement to the optimization function. So with that in mind, can we try to assemble what's going on here? Okay, what I remember from his lecture, and I watched this a while back, I watched it about a week ago, is that, you know, even though you get a distribution like that Gaussian over there, right, you're going to sample something from it. And that sample may not be at the mean. It could be off to the left or the right, okay? And that means the gradient is going to suggest not moving to correct for whether the sample was to the left or the right of the mean, rather than moving it towards the optimum, because your variance is, you know, pushed off more toward the side. Let's say it was over here, then the gradient would be this way. You'd be tending in the right direction. But if you pick one over here, the gradient would be going on the other side, and then you'd move in the wrong direction. So it's sort of dependent on which sample you pick. And if you keep on picking opposing samples, you're going to get this zigzag effect. Right? What you really want is the mean of this Gaussian to move here. If you're picking samples one time, you picked it over here, you move the Gaussian this way, you pick it over on the left side of the right side of the Gaussian, you move that way, right? So it's sort of dependent on your sample. Right? So if you take the natural gradient, you're correcting for that. I'm not that clear about it. That's my understanding. So maybe you guys can elaborate.
So there are two parameters here, k and sigma. In the first, with the first algorithm, it always points the k in the downward direction. So the k parameter is not improved by the algorithm, whereas with the natural policy, since we have the Fisher information, we know which parameter changes the probability, our pi. So it modifies k appropriately so that the policy takes that's.
Anyone externally want to try to give it a shot on explaining?
Vanilla policy gradient because of the way you sample, it's random sample, hence you have it needs Gaussian in nature, right? Because it's randomly sampled. And hence, because of that methodology, your gradients will push towards the so-called mean of what you've been sampling. But by taking natural policy gradients and using that Fisher information, adapting it towards that problem statement instead. Is that what it's trying to do? That's why you see the arrows of the natural policy gradient pointing towards the same point, because that's like adapted towards the problem.
Right, they're all trying to point and solve that optimality problem on the right-hand side of the diagram, right? Which is that you want to do gradient descent to the optimum, right? But because of the variability in your samples, you may get cases where the gradient at that one policy points in the wrong direction, right? So let's say you're close to optimum, your saddle point is, the gradient's very small, not very steep, right? So then if you take the Gaussian around the point near that stable point, the variability or the variance you would get from whatever policy you pick within that Gaussian would completely overwhelm the gradient towards the optimal policy, right? So then you're essentially having so much noise that the policy, the optimal direction towards the policy wouldn't come up well. All right, that's my understanding. And so the natural gradient is trying to correct for that. Lisan, do you not? Okay.
So this says that using a natural gradient is even practical. So here he refers to some papers. So this is our natural policy gradient. So it says it's generally good choice to get a stable policy, and cite some papers which derived. And then he says if we choose this alpha, it is a trust region policy optimization, which I don't know, probably covered in the next lecture. So if we choose this alpha, why does it become a trust region policy, or
so
what is
it? If you use a natural gradient with then your learning rate, which is alpha, you either pick by hand or you use random or whatever. So then it's called natural gradient policy. But then if you fix so we heard talk about epsilon, right? As long as it's the distribution is not within epsilon or repeat. So if you choose the epsilon and then you fix your learning rate by this epsilon, right? Then using natural policy gradient, it's what they call the trust region policy. So,
trust region. So to review, so we did a first order approximation for objectives. Then we, I'm sorry, what is he referring to here? Which slide? First order approximation to objective. Oh yeah, oh this one. To compute the gradient, we do first order approximation. Then we can take gradient step as in policy gradient, and then in this case we have a constraint because we're bounding the probability, the new theta, and then we so if we use KL divergence with Fisher information, it becomes natural gradient, and then we can use this algorithm. So anyone else want to summarize this better than?
Maybe we can look at some blogs that helps a lot. So Google is your friend. That's Google. Natural gradient.
How is that?
I was reading this while we were talking. Okay, so this is trying to summarize what they said in the slides, right? So in the original policy gradient algorithm, right, we're updating our network in the direction of the gradients, right? But the problem is, you know, we're trying to optimize it without any guarantees that the new network or the new policy is anywhere close to the beginning, right? So we don't want to do that. We want to say, well, don't go too far away because you might be jumping the gun, right? So we are going to use a replacement where we have this constraint. This constraint is saying that you know, the new network is going to have to behave pretty similar to our old network. We can tune that using epsilon, right? So our step size is going to correspond to some distribution of the network, not its values, which is what we were doing previously, right? We're doing theta prime minus theta. And so we're not doing that anymore. We're looking at the policy, the distribution policy, right? So we get something that's a more stable learning state because, you know, we're making sure that the distributions are close. Like Wee-san said before, it's not really vanilla gradient descent. It's more like gradient descent, making sure that your steps are pretty close together, right? So that's why it's more stable, right? So we call this natural gradient descent because you have that capability. And like we were saying about before, when we don't do that, when we don't do that, we get this problem here, where you know, when we're going back and forth and we're trying to optimize the policy, we may end up sampling something that's very far from the mean, or something if we're representing the policy as a one-dimensional Gaussian, and then the gradients there are going to be very different, you know, and the mean. So there's a problem there. That's why you need to go to optimization problem with this the constraint. So I don't know. I found some of the other blog posts helpful. If you find a blog post helpful, please put it either in the Slack or on the Google Doc, so we can put it into the so Slack a lot. We were just bombarding Slack with papers and blog posts and stuff like that. So that I think that that's very useful, is that we do this in tandem, and we don't just stick to the slides, because then you can get more feedback. Anyone else have any other things that they want to throw at this? Of course, we can't always trust blog posts. They're not always accurate either, but at least you can triangulate a little. Go ahead.
Yeah, I just have a kind of intuition, like, so my understanding is that natural gradient is like restrictive, like parameter changes, and in order to make a gradient more stable, but which means it might increase the risk of the falling to local optima.
Will it fall into a local
yeah,
optimum?
because like to avoid falling to local optimum, it should be better to like explore more like dynamical manner, as far as my understanding in parameter space. So.
Yeah, I think in general, any type of gradient descent, if it's a non-convex function, which almost everything we do is non-convex, then we're out of luck. We're going to converge to some local optimum. It depends on how terrible looking that manifold is, right? But you probably want to do some trade-offs, right? At the beginning, you may accept more of a natural, that's the wrong word, the vanilla policy gradient, where you allow yourself to make large steps in any direction. And when you think you're getting pretty close, maybe you don't want to trust the vanilla policy gradient very well, because it could bring you out of that place where you are just trying to fine tune, and then maybe using a natural policy gradient. It's sort of like the simulated annealing type of work that you would see in other areas, where you first have a large exploration parameter, and then you slow it down and say, okay, I think I've gotten pretty good. I don't want to explore so much. I want to optimize and get a good policy out the door. Right. So I think Sergey mentioned that a little bit. Like, you can trade off the two parameters, right, in the dual gradient ascent. I can't keep track whether it's ascent or descent, right? Yeah. Other questions or things you guys want to bring up? Are you comfortable with gradient, natural gradient? We have a half hour left, so we can just keep on talking about things until everyone's freshed out. It's better that people get something instead of, okay, I have these floating keywords I don't understand.
Is there a more technical block?
Yeah, I'm sure there is.
This one's sort of very.
What do we want to do? I can put in like Fisher information and see whether something comes out. Go. Any of these look promising? I also put some of these in the thing. I'll just stick with blog posts for right now. This one at least has equations. So those of you on remote, feel to just unmute and say something if you want. So this one has this nice diagram that's telling you why the KL divergence is better, right? So the idea is you have like two distributions, and even though they have a distance of 4 each, they're actually in a distributional sense quite different from each other, right? These two overlap significantly. These two don't even overlap at all, so the distance between them is fairly significantly different. Which is why if you use the Euclidean difference, right? The Euclidean distance would just measure it from the mean. You would still get a distance of 4, but if you use something like the Fisher information matrix or KL divergence, which is KL divergence is actually measuring the difference between two distributions in an asymmetric manner, then you would get a more reasonable approximation. Like the distance between this one should be less than the distance between this one, right? Okay. All right, so it tells you what the relationship between Fisher information matrix is with the KL divergence. Right, so it says claim Fisher information matrix F is the Hessian of the KL divergence between the two distributions. So like we were talking about covariance before, that's exactly right. Right, it's just you've got two terms, the entropy and the cross entropy. Right, the cross entropies are covariance. So that's that part.
Do we necessarily need to do this Fisher inverse matrix when we update? And look at the slide. So when you update data prime, you have data plus.
Which one?
On the slide 25. Yeah, this one. Yeah.
Let's go
so
back.
You have a data prime update here, which is the gradient sent by a natural gradient, right? So we actually need to calculate this. Can we use something like Adam instead? Like, can we just apply Adam on J data?
Yeah,
And use it to apply rather than doing Fisher? Is there any advantage or disadvantage?
We use Adam, that's why it's if it's Adam, then it's called natural policy. Because we were saying that the second last slide is like if it's Adam, then it's called natural policy gradient. But if you want it to be called the cross-region policy optimization, then you say you can use Adam as a learning rate. Something like that.
Oh, okay.
Because then Adam readjusts.
Okay. So it's just controlling that learning. So you still need to do that Fisher and Buzz.
I don't know. Maybe I can try to write what is the Fisher information actually doing.
Yeah, you want to go to the board?
I might be wrong, but
No worries. No, it's only being recorded and put on YouTube forever.
Yeah. Okay. So I guess like what are we trying out? So we're trying to change this, right? So then, well, we're saying that this kind of approximately equals to 1/2. Right? Yeah. So then they are saying that Fisher, well, right, intuitively is equivalent to a covariance matrix, I guess. So the probability of covariance matrix that is first of all symmetrical, and then it's like positive and indefinite. So I think by the probability that it's being symmetrical, you can actually decompose it into two matrices of the form like this by LU decomposition or like I think so. Yeah. So then you can kind of write this out into this form. Right? Less than. So now, but so you can cancel out like 1/2, you kind of cancel out because you can adjust epsilon, so it goes over here, and so yeah, you kind of just right. And then you sorry, I'm missing a key. Yeah. And then you group this together. Yeah, you multiply this into the transpose, and then it becomes like a different. Let's say. So this is corresponding to an optimization problem that will probably look something like this. Right. Yeah, so this is like this works out to be the same form that we're actually trying to get, and so this is equal to it looks like something like that. So that's equivalent. So but yeah, so that looks like an optimization form of something like this. But yeah, optimizing it over like kind of like a different at a different stage, and that's why you're adding they're doing it like -1. That's why you have to multiply the inverse. I don't know how this come about, but it's because this works out to be of the same form, similar to that form, and that's why you kind of have to multiply this in order to convert it back to that. I don't know. Does it make sense? It might not. But yeah, that's what we thought, like something that we might be doing.
Any thoughts?
Any comment? Any improvement?
So we'll put it on the Slack. Just give me a minute. I took a picture.
Did you mention why alpha will take that form? Why this square root 2 epsilon divided by grad if it's a coefficient? Can you mention why alpha take the take that form? Which one? Which one?
The trust one.
The alpha, yeah, that particular value. You mean the square root 2 epsilon divided by
Square root 2 epsilon. Oh,
you just say 1. So we can divide by.
They didn't be right, but they said that instead of picking alpha, you can use epsilon if you already have epsilon. But the derivation of the equation probably
Keep with epsilon.
That's a step size, right?
But this actually, but if you look at it, actually this by having to complete F inverse, actually this problem makes it very slow, right? Yeah. Because you have a large parameter scheme, you have a very large parameter space of many kinds of policies that you can take. Then inverting this matrix is quite a challenge.
I think they say that if you were to use their trust policy, I think one of the positive. But if you use their trust region policy optimization, you get you do have to calculate it, but you get both of it. The F inverse and then the whole alpha term together. With, yeah, that's optimized. Like you get them both using a figure. I don't know how many.
This is exactly what you're saying. You know, this is the one of the posts on trust policy, right? So they say the inverse of the Fisher is very expensive, right? You don't want to do that. Instead, you want to do something else, which I haven't gotten to, but you can take a look at that. Yeah, looking at the conjugate gradient instead. And that leads us to the algorithm that was hinted at the end of the lecture, right? The trust reason policy optimization. So I think Sergey is just trying to step us through, you know, chronologically through several different algorithms and their variants, right? So if we want to summarize, you know, the vanilla policy algorithm doesn't work very well because you get too far away from the policy, so you want to constrain. There's a KL divergence way of doing it that uses a local, the Fisher information matrix, but that becomes expensive, right? So you use a conjugate gradient method, and then you end up with something like trust reason policy optimization, which still gets the same gist. You know, it has the same spirit of the type of optimization, right? Yeah. So I think with all this precursor work, when you read the blog posts or you know, the archive papers on the original ones, maybe it'll make a bit more sense.
Yeah, I'm just curious. With the amount of approximations being made, does it ever steer off from the true objective?
I'm sure it does. I'm pretty sure people still think of RL, deep RL as black magic, right? When it works great. When it doesn't work, it explodes in your face and you get a nice fat electricity bill, right? So, you know, I don't think people really understand yet when things work and when they don't. I mean, even the deep mind folks, they show you the Atari games, like sometimes it explodes in their face and they're still not sure why.
But I think the convergence properties are good to get you results. Some get convergence all the time. Because there's thing we went through today, and especially some of the other things we did previously, there are a lot of approximation steps because you end up with things that are hard to approximate, but easier for.
So that's why I think the intuition is really important. I mean, if you just run the math, you might get the math, but then you don't know when things are exploding, right? Because you're just doing the math blindly. You know, you might be able to look at TensorBoard or something and say, okay, something's off, but why the heck is that going off, right? So developing the geometric intuition, I think, is pretty helpful.
And that's why we did the analysis of bounding the system. And in that he said that this is not a good bound as we go along the divergence in the
the T term increases.
Yeah, T term increases. It's not a good bound, but it seems to work.
Yeah, when we say seems to work, you know, it's always with quotation marks, right? No proof of convergence, can explode in your face, warning, dangerous chemicals, you know, hazardous weapons, etc. Yeah, 5 more GPUs. We don't know what we're doing, but we have lots of computation power to throw at the problem. So, yeah, I don't think we, you know, in any projects that we might do, we would actually conquer or try to look at the theory. But if you're an RL researcher, that's, I think, very promising areas to try to find out what's going on under the hood, right? Yeah. So with that, let me seg to how we are doing for projects. I can see that in the Google Sheet, we don't have many proposals for projects yet. So just to remind you, it was due today. So I'll give you until 11:59 p.m. tonight, okay, to go to the worksheet and then, you know, go to this column. This is column J, and then put in a project title. Okay, remember, by virtue of signing in and participating in this course, including everyone remotely, you are bound to actually do a project in this course and participate. Okay, so that means all of you who are listening, your names are listed here, and I can see some of you have put your bounding boxes on the slide. That's great. Please put a project title there. Okay, as we said, you know, we are doing these experiments in NUS in good faith, and you know, it really only helps if everyone participates. Okay, so we're not going to be, you know, very strict about it. You can't fail this course because you're not paying any money, but it makes it much more compelling if you do something this way. Okay.
You can also do the homework assignment.
Yeah, you can do the homework assignments. I just want you to go do something that you can talk with other people about. You know, if you just do Sergey's homework assignment, then you do it to a certain level where you can really understand, then it's fine. I mean, if you look at this course, it's not hierarchical or serial, right? It's sort of like 2 lectures that are serial, and then the whole thing branches out because there's too many different threads, right? There's policy gradients, there's the Q functions, all value estimation, right? All these things are sort of in parallel. So you know, it's a wide scoping course, so you don't really actually have to do very much. So if you just did a homework assignment for a particular deep reinforcement algorithm and then try to report more on it, I think that's okay for us. This is not really meant for MCs at this point. So if any of you don't have a better idea for a homework assignment, you could just say on the again on the project channel. I think there was at least one nice gentleman who decided that they would at least say something about that. You know, Joash from NTU, I think, said looking to do a meta reinforcement algorithm. So any of you guys want to just do a homework assignment? I want to do homework assignment number 1. Okay, then that's fine too. I think, have you looked at his homework assignments? Yeah, they're actually very well structured. I quite like them. Let's see, Rian. Homeworks. I don't know. Policy gradients. Why not? Okay. So he gives you the math again, and actually this is actually fairly helpful because this is like our notes except actually complete. And so they give you a problem, right? Okay, and then ask you to do some math. right? And then there's code. Of course, you can't get to the code. Oh, well, actually, you can. Okay, it's on GitHub, so you can actually do this. Yeah. So constructing the computation graph, which you need in TensorFlow, right? And then implement the policy gradient algorithm. Do some experiments. Then it tells you the flags. So that's pretty nice, right?
I think for some projects we need the simulator.
Yeah, you may not have the simulator for it. So yeah, you probably want to, before you actually do the homework assignment, check whether it's viable, right? Otherwise, you may need something else to do that. Yeah. Okay, but I think a lot of them, that there are half-baked extensions to some of the homework assignments. You know, lecturers like to do that. You know, you say, I don't know, but this sounds fun, so I'll just put it in an assignment. So you can try some of those other things, right? Okay, so pick your favorite RL weapon, you know, and then look at the assignment. That would be a good way to scaffold what you want to do for your own project if you want your own data or anything like that. Because these actually nicely compiled a lot of the notes that you might want for a particular lecture. Okay. All right, so next week is recess week. That doesn't mean we get to break. It means we get another lecture. Yay. So I think we have the gentlemen, I think they're all men at this point, on W recess week prep who are getting ready for the lecture. And those of you in week 7, those of you online who are week 7, please use the Slack channel to start coordination. Okay, so thanks. That's all we have for today. Let's thank all of our speakers today and our scribe.
I'll try to latex.